Hi, I'm Joe from TU Darmstadt, and I'm here to give a quick summary of our paper on controllers inference. So we're building on our previous work, input inference for control, or I2C, and this algorithm performs trajectory optimization via approximate inference on a probabilistic graphical model. And it does this by turning our control objective into a likelihood, and we do this through an exponential transform of the control cost function. And note that this introduces an unknown temperature term, alpha. With Gaussian I2C, we exploit the fact that when a cost function is quadratic, this makes this likelihood Gaussian, and this means that we can use existing approximate inference methods for specially designed for Gaussian message passing. And so I2C is an EM algorithm. The E step corresponds to Bayesian smoothing, which in the nonlinear Gaussian setting resembles regularized ILQG. And in the M step, we optimize our unknown model parameters, which in this case is this temperature alpha. And in the paper, we look at I2C, or various aspects of I2C from a more control theoretic perspective, and I'll summarize two here. So the first one is the role of feedback in nonlinear trajectory optimization. So like differential dynamic programming or ILQR, Gaussian I2C returns time-varying linear controllers. And while these provide stabilizing feedback, they're also quite brittle and can lead to quite bad local optima. An alternative is to use pure feed-forward, but this is bad in the stochastic setting as we don't get any stabilization. So what I propose in the paper is to use what I coin an expert controller, and this uses the belief in the state distribution that we have in I2C in order to interpolate between feedback and feed-forward. So if you look on the figure on the left, when the state is close to the mean, we apply linear feedback. But if the state moves away from the expected distribution, then we fall back to feed forward. And in practice, we found this really helped with balancing stabilization and getting good optima during nonlinear optimization compared to other methods. The second aspect is covariance control, and this is a stochastic control method where we do minimum energy, usually in the linear Gaussian setting, but now with constraints on the initial internal state distribution. And with linear Gaussian I2C, this is quite easy to implement. We just apply the terminal state distribution and iterate the E step. And we can even do it in a nonlinear setting too quite easily. On the left, we apply covariance control to a nonlinear pendulum swinging task. So in summary, we can use I2C to improve local linear controllers for trajectory optimization, and inference also makes covariance control easy. Thank you for listening.
Hello, my name is Yujito. I'd like to talk about stochastic optimal control. We focus on a polynomial cost function and linear system with time-invariant stochastic parameters. Let me introduce the problem setting. We consider a linear stochastic system and linear feedback control with the state x and input u at the time. The stochastic parameter is unknown and constant. Its probability mass function is known. The feedback gain is constant that cannot use the unknown parameter. The system matrices are known function. The cost function consists of a polynomial of the state and input over the infinite time horizon. Our main problem is to find an optimal feedback gain to minimize the expectation of the polynomial cost function. The proposed method employs the gradient method to design a local optimal gain. A challenge is to obtain the gradient of the cost function. This is very difficult because the cost function consists of the infinite sum of the polynomial. Moreover, the expected cost involves high-order stochastic moments, which are hard to obtain for a large time step. To overcome these difficulties, the expanded polynomial matrices are introduced using the closed-loop matrix, feedback gain, and Kronecker products. In the main results, we derive the gradient of the expected polynomial cost function as a linear function of the expectation of this term. This term is easy to calculate because it consists of the polynomial functions and their derivatives. We show the simulation results. Various values of the cost occur, depending on systems with different stochastic parameters. In terms of the expected cost value, the proposed method outperforms a quadratic regulator and deterministic optimal controller. We designed a feedback controller for linear systems with unknown stochastic parameters to minimize the expected polynomial cost function. Our main result provides an explicit gradient of the cost, so it is easy to calculate the gradient and use the gradient method for optimizing the feedback gain. Thank you for your kind attention.
My name is Jiahao Shi. This is the work I did with Professor Small, and we are both from the Johns Hopkins University. We developed an algorithm called SQP-based projection SPSA to solve general stochastic optimization problem with inequality constraints. The problem setting we are considering is constrained, and the constraint set is defined by general deterministic functions. The problem is also considered to be stochastic and derivative-free. These two natures of the problem motivates us to think of SPSA algorithm, which only requires two function measurements per iteration. Both existing methods have their potential drawbacks. When the constraint functions are designed to be complex, as the picture shows, it's difficult for the projection methods to compute the projection operator. As for the penalty function method, it cannot deal with hard constraints, since the iterate could be outside the constraint set through the optimization procedure. Considering these drawbacks, we developed an algorithm. The basic idea is that we modify the projection SPSA algorithm, rewriting the projection step as a projection subproblem. This is actually a constrained nonlinear optimization problem, and we could use nonlinear programming techniques to solve it. We choose to use SQP to estimate the solution, and we prove the convergence of the algorithm in our paper. We then apply the proposed method into a numerical example, where the constraint set is designed to be very complex. As you can see, the standard projection-based method could fail in this problem. We compared the results for the proposed SQP-based projection algorithm with three popular penalty function methods in terms of the average error and the amount of constraint violation, which is determined by this Q function. The results shows that the proposed method has less constraint violation compared to penalty function method. In conclusion, our method is more advantageous than prior methods in that it can deal with complex constraint functions, it can deal with hard constraints, it may have less constraint violations, and also, it's very easy to implement. If you have further interest in our paper, please scan the QR code to download the full version of the paper. Thank you.
Hi, I'm Bhagishri Telsam. Over the next few minutes, I'll quickly talk about our paper on numerical evaluation of exact person-by-person optimal nonlinear control strategies of the Witzenhausen counterexample. Let's begin this by talking about what the counterexample is. So it was introduced by Hans Witzenhausen in late 1960s. It's a two-player problem. As you see, gamma 1 and gamma 2 are the two controllers. X0 and V are the external inputs, which are random. And V is standard normal distribution. And the parameters in this design are K and the parameters of the probability densities of X0 and V. Now, what makes this problem interesting is the information pattern here. Well, you see X0 is known to gamma 1 directly. It goes to gamma 2 through X1, and X1 is X0 plus U1. So the action taken by the first controller influences the input to the second controller. And that's what makes this whole information pattern for this counterexample non-classical. And depending on the values of the parameters k and the parameters of PDF of x0 and v, the optimal laws are sometimes linear and sometimes nonlinear. It depends on the values of these parameters. So far in the original paper, Hans Witzenhausen found the optimal gamma 2 given gamma 1. And then in the parameter region where the optimal laws are linear, he has derived what those exact optimal affine laws are. However, in general, in the nonlinear space even, the optimal gamma 1 was unknown for a very long time. And then eventually in 2014, Haralambos and Ahmed came up with the optimal person-by-person laws for both gamma 1 bar and gamma 2. Gamma 2 was already known. And it looks like this. You can see these are two integral equations. They are coupled and they are nonlinear. So given certain value of x0, how do you find out what gamma 1 bar is at that value? And accordingly, what gamma 2 would be at that given x0 and that specific v. So to compute this, we use something called as Gauss-Hamite quadrature approximation. It basically evaluates the integral as a summation, and then we rewrite the equations for gamma 1 and gamma 2 in this approximation form and pose this as a system of nonlinear equations and then solve this. I'd be happy to talk more about the entire detail through my poster presentation. Thank you.
Hello everyone, my name is Jing Zhang, and I will be presenting the work titled Stochastic Model Predictive Control Using Simplified Affine Disturbance Feedback for Chance Constraint Systems, which is done in cooperation with Toshiyuki Otsuka. The motivation of our work is that optimizing over open-loop control sequences in SMPC directly leads to very conservative control performance and may be infeasible when a constraint exists. Therefore, a control policy known as affine disturbance feedback can maintain the closed-loop prediction and convexity of optimization problem. But the main drawback of the affine disturbance feedback is its high computation cost. In affine disturbance feedback control policy, the number of control variables grows quadratically with prediction horizon. To solve this problem, we proposed a simplified affine disturbance feedback control policy this time. The matrix form of the control policy can more clearly show that in original affine disturbance feedback, the matrix M contains decision variables in quadratic levels. In our proposed method, the matrix M has a strictly lower triangular Toeplitz structure, which contains fewer decision variables, and just grows linearly with respect to the prediction horizon. The proposed method also provides equivalence property to a certain state feedback control policy. We can guarantee the feasibility and convergence to a given disturbance invariant state with probability 1 due to this equivalence. This work is implemented to a building temperature system example. The control target is to keep the room temperature above 21 degrees centigrade with minimum energy. For comparison, the open loop control policy, ADF, and the proposed ACADF are implemented here. The control performance in the left figure and the first table shows that the open loop control policy leads to conservative control behavior. In contrast, ADF and ACADF leads to similar control behavior, but ACADF slightly more conservative than ADF. The next table shows the computation time of these three controllers. The table shows that the computation time of open loop and SADF do not grow so quickly as the prediction horizon increase, while the computation time of ADF grows very quickly. Our method provides a good balance between computation time and control performance in this example. Thank you for listening.
Hello everyone. Welcome to a presentation of our paper, Cooperative Test Integral Control for Stochastic Multi-Agent Systems. I'm the presenter, WeA01. Multi-agent system requires each agent to intelligently make its own decision, and it is commonly exists in our world. Distributed control is a method to manipulate multi-agent systems, according to whether a final common behavior is given. We can divide them into two categories, and in this paper, we will mainly focus on the distributed passenger control without a given common behavior. In order to overcome the current challenges in this area, we propose a distributed control framework that only requires moderate computation and communications, and considers the cooperation between neighboring agents. Our distributed framework decomposes the original system into multiple subsystems, each of which consists of a central agent and its neighboring agent. The local optimal contraction of the central agent is obtained by minimizing the cost function in its subsystem. The dynamics, running cost function, and value function of a factorial subsystem are given in this slide. In this theorem, we give the formulation of the stochastic HJB equation and the analytical form of the local optimal control action. By using the Feynman-Kalk formula, we can solve the stochastic HJB equation by an expectation of diffusion process evolving forward in time. We evaluate the closed-form desirability function and optimal control action. We discretize the time span and approximate their analytical solution with path integral formulas. Here, we show the path integral formulas for the optimal control actions and the optimal path distribution, and the integrals can be approximated by using the Monte Carlo method. This is the cooperative path integral control algorithm. The planning and execution of each agent are fully decentralized. In the simulation examples, we first consider a team of 3 UAVs, and we want UAV1 to fly closely with UAV3. Here we give the UAV dynamics and the running cost functions. In these figures, the solid line are the trajectory and distance subject to the distributed framework and the joint cost function, while the dashed line are the results subject to the fully factorial cost functions. We can see that our method can significantly reduce the distance between UAV1 and 3. We also test our method with obstacle avoidance and the larger scale of cooperative UAV team. In the end, we also want to acknowledge the support from NSF, Air Force, and VJU UIUC Institute. Thank you for your listening.
Hi, I'm Krishna Kalagarla, and today I want to talk to you about my work, Optimal Control of Discounted Reward Markov decision processes under linear temporal logic specifications. This work was jointly done with Professor Rahul Jain and Professor Pierluigi Nuzzo at the University of Southern California. The motivation for our work is that many real-world applications like autonomous driving, surveillance drones, etc. must satisfy multiple objectives in order to complete their tasks. They further operate in uncertain environments typically modeled as Markov decision processes. There also has been increasing interest in expressing such complex mission objectives unambiguously by temporal logic, which is a temporal extension to propositional logic. In our work, we focus on composite tasks where hard objectives like safety, reachability, etc. are expressed in linear temporal logic, and soft objectives like fuel consumption, comfort, etc. are expressed as a reward function. The objective is then to find an optimal deterministic policy which maximizes the expected total discounted reward, such that the given general LTL specification is satisfied almost surely. Earlier work has focused on either steady-state behavior by optimizing average reward, or transient behavior by considering a total reward objective under co-safe LTL specifications. In our work, by considering discounted reward optimality, we consider both steady-state and transient behavior. We also allow for any general LTL specification. Our solution approach is that the given MDP and an automaton equivalent to the LTL specification, we construct a product MDP expressing the reward objective and another modified MDP expressing the LTL objective as a reachability criterion. These are then expressed as linear constraints and objectives in terms of different occupancy measures. These occupancy measures could possibly refer to different policies and thus are connected to a single policy in a novel manner, resulting in a mixed integer linear program, whose solution gives us the desired optimal deterministic policy. Our formulation can also handle additional constraints in terms of lower bounds to expected discounted returns with respect to different reward functions. I'm looking forward to the opportunity to discuss our work in greater detail in the poster session. Thank you.
Hi everyone. In this talk, I will present our recent result on the deep learning-based real-time, robust, and optimal estimation and control framework for stochastic nonlinear systems using the concept of neurostochastic contraction metrics. We call it an NSCM in short, and the NSCM Python package is available on GitHub in this link. The systems of our interest are input applying nonlinear systems with stochastic disturbances W. And our goal is to develop a real-time state estimation and feedback control framework for these systems. This framework constructs a contraction metric, which can be viewed as a generalization of Lyapunov functions in the context of the differential dynamics of nonlinear systems in order to guarantee exponential stability. It is also optimal in the sense that the metric minimizes mean square distance between the estimated and actual trajectory for estimation and control and desired trajectory for feedback control. Also, the contraction condition for stability when designing the contraction metric provides robustness to stochastic disturbances. And finally, we model the metric by a spectrally normalized neural network to enable the real-time computation of the optimal control and estimation policies. Okay, let me briefly visualize how this framework works in practice. In the frame phase, we sample contraction metrics at each state by solving a convex optimization problem, which minimizes mean square distance between the estimated and actual or control and desired trajectory subject to the contraction condition. We do the same for every state. And once we have enough samples, we model the metric by a spectrally normalized neural network. Please note that we should get two networks for estimation and control respectively. In the online phase, using the measurement available at time t, the agent computes the estimated state x hat by using the estimation neurostochastic contraction metric. Also, given the state and the desired trajectory, it computes the optimal feedback control policy U using the control neurostochastic contraction metric. Since it requires only two neural net aberrations at each time step, the NSCM optimal control and estimation policies are executable in real time. We model the optimal contraction metrics sampled offline by a convex optimization using a spectrally normalized neural network. And then compute the optimal control and estimation policy using the trained neural networks or neural stochastic contraction metrics.
Hello, my name is Shengfang, and I'm currently a postdoc with Professor Chen Zhi at New York University. In this talk, as the title indicates, we will focus on using information theory to analyze the fundamental limits of feedback systems, including control systems and systems beyond control. Information theory was originally developed as a mathematical theory of communication, but it turns out that it can also be applied to analyze control systems. In this talk, we consider such a generic single input and single out feedback system, where D is the disturbance, E is the error signal, and G is the open loop system. By generic, we mean that the G can be any deterministic or randomized functions or mappings as long as it is strictly causal. Even with such general assumptions, we can prove that the IP norm of error signal E is always lower bounded by the conditional entropy of the disturbance D in such a way. For those of you who are not so familiar with information theory, you can simply think of conditional entropy as the amount of uncertainty contained in the disturbance D, and a mathematical definition can be found in the poster of this talk. On the other hand, we may also examine the conditions for achieving the lower bounds here. Moreover, further discussions and interpretations can be found in the poster as well. Note now that this generic setting may represent basically any feedback control systems where D can be the sensor noise or accelerator disturbance, and the controller and plant can be any deterministic or randomized functions or mappings. We may examine further the case of LTI plants with generic controllers, and the results can be found in the poster. Note that for all the results in this talk and in the poster, the lower bounds are valid for not only conventional control methods, but also, for instance, learning-based control. This means that, for instance, limits exist in general to what machine learning can do in feedback control systems. On the other hand, the generic bounds go beyond control systems. For instance, state estimation systems are inherently feedback systems as well. And recursive algorithms such as optimization algorithms are also essentially feedback systems. We're currently examining the implications of the results in such scenarios, and if you are interested, please feel free to contact us. And that is all for this talk. Thank you.
Hello, everyone. My name is Adam Thorpe, and today I'm going to be presenting the paper titled Approximate Stochastic Reachability for High-Dimensional Systems by myself, Vignesh Sivaramakrishnan, and Dr. Miko Oishi at the University of New Mexico. We consider solving the first sitting time problem for stochastic systems with arbitrary stochastic disturbances and seek to compute the probability that a system will reach a target set at some point in the time horizon and stay within a designated safe set for all time up until that point. However, without statistical knowledge of the disturbance, this problem is intractable. Instead, we approximate the stochastic reachability backward recursion by modeling the distribution as an element in a reproducing kernel Hilbert space using data collected via system observations. In the kernel-based approximation, we replace the intractable integrals in the backward recursion with Hilbert space inner products. As we can see here on a discrete time double integrator system compared to the traditional solution with dynamic programming, the kernel-based approach provides a close approximation of the safety probabilities. We can see that the two solutions are very close, with the maximum computed error being approximately 5%. This approach has several advantages, namely that it is largely resistant to the curse of dimensionality, and because it is data-driven, it is able to handle arbitrary disturbances and converges to the true solution as the sample size increases. However, the leap to extremely high-dimensional systems presents a significant challenge. In order to accommodate systems with high dimensionality, we employ a kernel-based speedup technique known as random Fourier features, or RFF. The kernel-based approximation using RFF provides an estimate of the safety probabilities that is more computationally efficient for high-dimensional systems, but at the expense of increased approximation error. Here, the maximum error is approximately 9% using RFF. We demonstrate this technique to compute the safety probabilities for a swarm of 170,000 planar quadrotors and form a concatenated system with over 1 million dimensions. The quadrotors are controlled via a reference tracking controller to take off and reach a certain altitude without leaving a vertical safety tube. And here we show the safety probabilities of a single quadrotor computed using the kernel-based technique under different disturbances to simulate wind. This system is far beyond the capabilities of traditional dynamic programming, but we enable tractability using our kernel-based approach. Using RFF, the computation of the safety probabilities for the concatenated system took approximately 45 seconds, while without RFF, the computation took about 1.2 hours. In summary, we have employed a kernel-based approximation in conjunction with RFF to enable tractability for stochastic reachability problems for high-dimensional systems.
Hello everyone, my name is Bolan Dai, and I'm presenting state-constrained stochastic optimal control using LSTMs. In this work, we consider the system with dynamics as shown in the first equation, under the costs shown in the second equation. The state constraint is given such that CSX can be a nonlinear function of the state. Also, control saturations are taken into consideration. For details regarding this formulation, please refer to our paper. To solve this problem, we first incorporate the constraints and saturations into the cost function. Then the problem can be written as a forward-backward stochastic differential equation. We then use the deep FBSDE algorithm to find the optimal control at each time step. This approach is easier to scale to high dimensions and helps with reducing the approximation error in both the value function and system dynamics. To incorporate the state constraints into the cost function, we can use a penalty function. The penalty function we choose in this paper is given as px. Additional to the constraint boundaries, we have an additional variable k regulating the steepness of the constraint boundaries. Also, we can substitute the quadratic control cost with the cost shown in the bottom when considering control saturation. After including the state penalty and control saturation, we have the new cost function as shown in this slide. We can write the problem in the form of a forward-backward stochastic differential equation, where the control at each time step is a function of the partial derivative of the value function with respect to the state, Vx. We use a neural network to learn Vx when given the current state. During training, we use a L2 loss between the terminal cost and the estimated cost to go at the final time step, and we use LSTMs, which are chosen to address the cursive dimensionality, nonlinearities, and long time horizons. We found that starting with a steep penalty function creates numerical instabilities. Therefore, we prefer to increase the steepness gradually. We use the square root of variance of the cost of each run over a fixed number of iterations as the updates threshold. We perform these updates until the state constraints are respected by the learned controller. We show the efficacy of our approach on a cart pole swing up task, where the cart position and cart velocities are constrained to be within a region. We see that our learned controller is able to swing up and balance while respecting the constraints. Also, we see that as we increase the steepness of our state penalty, the velocity curve gradually retreats into the constraint boundaries. To show that our approach is also able to deal with nonlinear state constraints, we limit the total energy of the system, which is the sum of the kinetic and potential energy. We see that our learned controller is able to respect the constraint boundaries. Thank you for listening to this presentation, and for more information, please refer to our paper.
Hello everyone, my name is Ali Pakniat and I'm a postdoc at the Institute for Robotics and Intelligent Machines at Georgia Tech, working with Panos Siotras. The title of our paper is Steering the State of Linear Stochastic Systems, a Constraint Minimum Principle Formulation. In this paper, we studied optimal control problems for stochastic systems where pinpoint delivery of the state to a desired value is a requirement and where the allotted time horizon is finite. A representative example is the landing of reusable rockets, which are required to come to full stop, i.e. zero velocity, at the exact coordinates of the landing platform and in the upright vertical configuration. We first studied the general nonlinear case and proposed to enforce a constraint on the conditional expectation of the terminal state under filtrations at all intermediate times. This transforms the problem into a non-classical stochastic optimal control problem where the cost is infinite for input policies failing to meet the expectation requirements. In order to solve these problems, we proposed the use of a version of the stochastic minimum principle, which we call the terminally constrained stochastic minimum principle. This requires us to solve these forward-backward stochastic differential equations whose numerical determination is, in general, computationally expensive. So, for the special case of linear stochastic systems, we derived closed-form expressions for the adjoint process in terms of the system's state transition metrics, its controllability Gramian, and the associated Riccati metrics. As you can see in these examples, the state successfully achieves the desired value almost surely, despite the presence of large dynamic uncertainties. However, this comes at the expense of potential use of large input values in order to counterbalance the effect of noise. If you are interested to learn more, please do not hesitate to reach out to me in the Q&A session. You can also contact us at the email addresses provided here. Thank you very much.
So the title of my presentation is Convex Approach to Stochastic Optimal Control using Linear Operator Theory. So in this talk, we're going to study the stochastic optimal control problem for a stochastic dynamical system of the form 1. For simplicity, we assume that the system has a single input and a noise enters the system multiplicatively, and it's of a vanishing time. That means at x equal to 0, the noise vanishes, and x equal to 0 is assumed to be the equilibrium point. The notion of stability that we're going to use in this talk is this almost everywhere, almost sure stability, which essentially says that x equal to 0 is almost everywhere stable if a set of initial conditions for which the 2 is not true is a measure 0 set, where the underlying measure is mu. So following is the optimal control problem given in equation 3 and 4, where the equation 3 is we define the cost function, which is defined with respect to measure mu0 and involves both the spatial and temporal integration and is subject to the dynamical constraint of 4. So this cost function can be written in terms of a well-known cost function v of x, which is standard cost function using optimal control. G of mu0 can be written as in terms of the integral v and d mu of x. We assume that the state cost is bounded away from the origin, and then there exists a feedback control for which the cost function is finite. Furthermore, the optimal control is also feedback in nature and is C4 function of x. With this, we can write down the optimal problem in the equation 5, obtained from equation 3 and 4 by substituting u equal to k. And following is the main results of this work, which shows that the optimal control problem, as defined in the previous slide, equation 5, can be written as the following convex optimization problem, where the decision variables are rho and rho bar. The cost itself has a structure of quadratic over linear and hence convex, where the constraints are actually linear in rho and rho bar. The feedback control is obtained from rho and rho bar using formula 7. And the feedback controller, the optimal feedback controller, is also guaranteed to be almost everywhere, almost sure stabilizing with respect to measure mu0. Thank you.
In this work, we study covariance steering of discrete time stochastic linear systems based on Wasserstein distance terminal cost. In our problem formulation, the system dynamics in equation 1, initial and desired state distribution, problem horizon, and the stochastic noise intensity are given. The main goal of this problem is to find a control policy to steer initial distribution to the desired one in finite time using the information of state history. To enforce the specification on terminal distribution, we utilize the square Wasserstein distance, which has a closed form expression for Gaussian distributions that are given in equation 2. In this slide, we present the precise problem formulation. The parameter lambda that appears in the objective function determines the weight between terminal distribution error and the total control effort. The main contribution of this work is to cast this problem as a difference of convex functions program. In order to do that, we assume affine state history feedback control policy in equation 4. Then we concatenate states, inputs, and disturbances. And we write the relationship between concatenated vectors in equations 5a and 5b. Using the bijective variable transformation in the equations 6a and 6b, we obtain the expressions of the expectation and the covariance of the concatenated state vector in equation 7 after some algebra. We can show that the objective function of the problem 1 can be equivalently represented as in equation 8 using the variable transformation in equation 6 and the expressions in equation 7. We show that the functions that make up the objective function j are all convex, thus j is a difference of convex function due to the last term j4. Finally, if the new decision variable theta is considered to be a Bloch-Lower triangular, the original state feedback decision variable k becomes Bloch-Lower triangular. Thus, problem 1 and 2 are equivalent. To solve the problem 2, we use the convex concave procedure, which is guaranteed to find local optima for the difference of convex functions programs. Figure on the left illustrates trajectory samples from the optimal state process after solving the problem, and the figure on the right shows the graph of the terminal covariance error versus increasing lambda for different noise intensity. The table reports the comparison of computation times of our approach with the off-the-shelf solvers on different problem instances. We observed that the proposed convex concave procedure-based approach is at least 3 times faster than the general purpose solvers. In this study, we showed that the covariance steering with Wasserstein distance problem is shown to be a difference of convex functions program under suitable variable transformations. This problem is solved via the convex concave procedure and shown to be more efficient than the off-the-shelf solvers. In the future, we plan to study the existence and the uniqueness of the solutions and extend our approach to nonlinear stochastic systems.
In this video, I will briefly present our paper entitled On a Notion of Stochastic Zeroing Barrier Function. My name is Pratama, and this is joint work with my colleague Dr. Binhu and Dr. Yul Nazaruddin. So the objective and problem statement. The goal of this paper is to propose a notion of stochastic zeroing barrier functions, or SZBF, for verifying the safety property of the sample path of stochastic differential equations defined in the sense of Ito. The main finding of the paper is that the zeroing barrier function concept in deterministic systems proposed by Ames in 2019 can be extended to formulate a safety verifications approach based on stochastic zeroing barrier functions for stochastic system defined by stochastic differential equation. Okay, the problem statement, we consider stochastic differential equation, or SDE, as in equation 1. Solution is defined in the sense of Ito, and we also consider the so-called infinitesimal generator of SDE1 given by equation 2, defined by operator lambda and a twice continuous differentiable function h in here. The objective of the paper is to characterize the stochastic invariance property of a particular set with respect to the SDE in 1. So this is the same approach as taken by Ames in 2019 for the deterministic system. The approach that we took in this paper is that to consider a set C defined in equation 3 by constructions that is a level set of functions h in here. And our goal is to establish condition on the defining function h of the set C that will guarantee that C is stochastically invariant with respect to the strong solution of the Ito SDE1 as given in equation 4. Our idea to solve the problem is that to show that if HXT, which defines set C in 3 is as CDF, then the set C is indeed stochastically invariant. And for this purpose, we define in this paper the notion of stochastic zeroing barrier function, or SZBF. So HXT, as in equation 3, is SCDF if there exists an extended class A function alpha and a set T, which includes the set C in equation 3, such that equation 5 is satisfied. So in equation 5, the first part is similar to the deterministic system, and the second part is our additional conditions, which consider the diffusion part. So the main result of the paper is given in 2 proposition and 1 lemma. Proposition 1 in here essentially define that the existence of stochastic zeroing barrier functions implies the stochastic invariance of the set C, as we previously defined. The second lemma essentially shows that the condition that we derive in this paper includes the condition for the deterministic systems if we set the diffusion part of the systems equal to 0. So we recover the result in deterministic systems. And the last one is the proposition which shows that the existence of a stochastic zeroing barrier functions also implies the stochastic stability of the set C. Thank you.
Hi, myself Indrajit, a PhD student at IUR, IIT Bombay, India. Is joined to work with Suyok, Kushbu, Kavita, and Kuanian from New York University. Topic here is controlling fake news by collective tagging, a branching process analysis. We all know what is fake news. This is misinformation spread over the social network. It has varying degrees of impact, ranges from social environment to political environment. Typically, when a user visits the online social network like Facebook, views some post in his timeline, depending upon the attractiveness of the post, the user shared the news to his friends and his friends of friends, and so on. This is how a news item propagates over the network, but the users have doubt on the authenticity of the news, whether it is fake or real. In this work, our aim is to identify the fake news using control mechanism alongside do not influence the real news propagation. Our proposed warning mechanism relies on 3 pieces of information: system-generated warning, sender tag, and user intrinsic capacity to identify the fake news to some extent. It may not yield perfect detection, but collective tagging of the users has a feedback effect to the system-generated warnings, and which can further improve to deter the fake news. The situation is well captured by the multi-type branching process like news generates, shared, and dies after some time. The pair xt, yt represent the number of fake and real tag at time t. The equation 1 represents our control warnings. WB are the corresponding control parameters, and beta t represents fraction of fake tag at time t. Under the warning mechanism, the users share the post by tagging it as a real or fake. The systems evolve continuously. When a user receives the fake tag, it decides the tag and share among his friends. The system evolves according to these equations, where it tag it dies down, hence -1, and produces a random number of copies of the post. When a user receives a real tag, the dynamic similarity can be explained. This kind of dynamics lead to a population size dependent continuous time branching process. Using stochastic approximation tools, dynamics converges to the following limits: either use dies or population settled to a unique proportion. We define two appropriate performance measures. The type 1 performance is the expected fraction of user mistag the fake news, while type 2 is performance is for the real news. Now, how to find these control parameters? In practice, adverse effect on real news propagation cannot allow it beyond a certain limit. So, we concentrate on the side rule. Under certain conditions, the optimization problem reduces to one-dimensional optimization problems. We plotted optimal type 1 performance as a function of the tolerance parameter C. In the same figure, we also plot the results of our type 1 performance obtained from the Monte Carlo simulations. For instance, when 2% users are allowed to mistag the real news, then there is only 10% of users tag fake news as real, whereas uncontrolled setting, a huge percentage of users mistag the fake news. This is our key contribution. Thank you.
Hello everyone, I'm Lu from Department of Electrical Engineering, University of Texas at Arlington. I'd like to introduce our work about the reduced order estimation of the uniform, completely connected, homogeneous influence model. First, let me introduce some backgrounds of our study. The influence model is a discrete-time stochastic automaton that captures spatial-temporal network dynamics. It consists of a reduced-order representation of networked Markov chains and has found broad stochastic network applications, for example, power grid and social network. Parameter estimation from observation data is critical for its applications. The performance of existing estimation methods have some sorts of limitations, for example, high computational cost. Here we take a structured approach to study reduced computation estimation methods for IM, and we first focus on a canonical class of IM, the UCCHIM, where all sites are fully connected, with common mutual influence and local status update rules. Next, the main results of our study. The key idea is that we construct a reduced order Markov chain representation through exploiting its symmetrical network topology. 4 theorems are proposed as shown here, and the parameter estimation algorithm is developed based on theorem 4. More details can be found in our paper. With N and M denoting the number of sites and the number of status for each site, respectively, it can be seen from this figure that the computational cost is significantly reduced using our proposed reduced order Markov chain. We would like to thank the research support from NSF and ARO. Some references are given here. Thank you for watching.
Hi, and welcome to the poster of our paper entitled Compositionality of Linearly Solvable Optimal Control in Networked Multi-Agent Systems. Optimal control for stochastic systems is typically difficult and expensive to compute, especially in high-dimensional cases. Meanwhile, dimensionality of a networked system grows exponentially as system state scales. Therefore, determining the optimal solutions to stochastic system control problems in the multi-agent systems remains challenging. In this paper, we proposed a distributed control framework to factorize a networked multi-agent system and investigated the control compositionality in the linearly solvable optimal control setting. In the problem setting, we considered dynamical systems modeled by transition probability in discrete time and ito diffusion in continuous time. The cost function penalized both state cost and control action effort. Optimal control solutions can be reduced to a linear form. For networked systems, we factored out one central agent and its connection with the neighboring agents in each factorial subsystem. To consider the compositionality of optimal control laws, the component problems need to share identical dynamics, cost risk, interior state size, and terminal state size, whereas differ at the final cost. We further extended the compositionality to different terminal state scenarios to explore the composite control generalization in this work. The composite control law can be computed directly using the component problem solutions without resampling. We evaluated our proposed method on a cooperative UAV team, both in a file-by-file grid flying environment with obstacles and a goal-reaching task in continuous time. The composite control law can be obtained in direct computation efficiently in both cases, which solves a new problem accurately in the former scenario and generates acceptable error in the latter scenario. Thank you very much for listening, and I look forward to your questions or remarks.
Hello, my name is Rafael, and I will give you a 3-minute pitch about our work. This work is entitled Stochastic Safety of Random Dynamical Systems. Imagine standard task of control in some industrial settings. In each of these tasks, we have some objectives to be reached, some goal to be reached, but at the same time, we want to avoid forbidden states. We want to have a control with some constraints. It could be a robot that wants to reach a goal without hitting any obstacles. Suppose that the system is also a subject to uncertainties. Not only the system by itself, but also obstacles have some random character. That is, the obstacles are random sets. Think about a ship. It sails to a harbor, but it also has to avoid collision with other ships. These are the random sets. So such situation I have just described will be modeled by a random dynamical system, and the forbidden sets will be indeed random. Actually, the paper shows what safety in this context is. This is the probability of hitting the forbidden set before reaching the goal. Hopefully, this is very small. This concept we call in the paper P-safety. The core of the solution to P-safety is so-called Dirichlet problem. Dirichlet problem is an integral differential equation with known boundary condition. This is a pretty difficult problem. That's why we go a bit different way. We solve P-safety with the use of concept of stochastic barrier. They satisfy two conditions. They are to be supermedian, but at the same time, they are also satisfying certain separation conditions. In short, what paper is about it is we derive some algebraic conditions that help us to assign probability of hitting the obstacle before reaching the goal. Thank you very much.
Hello everyone, this is Mohammed Mubarak and I'm a graduate student at George Mason University. Our research is about stochastic versus deterministic modeling for the spread of COVID-19 in small networks. In our research, we try to understand the different models that can describe the spread of COVID-19 between single individuals in small networks. Now, talking about the idea of multi-scale spread in a network and considering the graph theory, each node in the graph can represent a single individual or subpopulation. While most studies are interested in the spread of the virus in a population networks where each node in such a network is considered to be subpopulation, a question is raised here. How does COVID-19 spread in small human contact networks if we consider that each node in such a network is a single individual? To answer this question, we consider the SEIR model and we propose the stochastic and the deterministic version of this model. And our choice to the SEIR was because of the important artifact of the incubation period in COVID-19, which can be captured by the exposed state in the SEIR model. As we have introduced the stochastic and the deterministic version of the SEIR model, a question is raised here: which model is right for the spread of COVID-19 between single individuals if we balance between the tractability and the accuracy of the model? To answer this question, we presented an example of 7 staff workers and 28 seniors in a nursing home, where first we analyzed the 7 staff workers network and we assumed that person 4 was discovered to be infected at day 0. And we were able to answer questions like, what is person 2 chance of becoming infected 12 days later from now? And which model is the most accurate to use in such an example, and why the deterministic models won't help as much in such an example? Also, considering the 35 people network in the nursing home, we answered a question like, how does the aggregate numbers of infected differs using the different models? To show you the results that we got and answer these questions, I'll see you on the poster session. Thank you.